Now we're interested in going over the electric potential distribution due to charged objects. This lesson should bring back a lot of memories to when we were finding the electric field due to a continuous charge distribution. What we realized was that we had to integrate the electric field as if there were tiny point charges with charge dq throughout the entire object. With electric potential, the situation is quite similar, except for one main difference. The electric field is a vector, so we had to evaluate an integral involving a vector r hat. If you remember, it led to some hairy, in some cases nightmare-inducing situations. But with the electric potential, we ain't got to deal with none of that. Instead, the electric potential is just a scalar, so we're just adding up numbers anytime we need to find the electric potential due to a bunch of individual point charges. So the integration itself is much simpler. If you have some charged object then, and we're interested in the electric potential at some point, all we have to do is evaluate the integral over that entire object of k dq over r for every dq that's a part of the object. That's really all there is to it. There's no fancy direction or unit vectors we have to account for like before. I know you would much rather work with a scalar integral than an integral involving vectors because that brings back a lot of memories to your calculus classes where all you're doing is evaluating integrals with scalars, no vectors attached. So let's try an example. We're actually going to try the same example we did with the electric field, but see how much easier it is if we're only concerned with the electric potential instead of the electric field. Imagine we want the electric potential at the center of some charged ring. If we wanted the electric field at the center of this ring, then by symmetry it's just zero. We saw that when we were going through the electric field lessons. But now we want the electric potential, so it's not necessarily going to be zero at this point. If the ring is thin enough and has some radius r and charge q, then the electric potential might be given by this integral we see here, where little r is the distance from the center to any point on the ring, and dq would be the charge at that point on the ring. But we see that the distance to any point on the ring is always going to be capital R. So we can actually pull that out of the integral here, and we're left with this snazzy looking integral here. Evaluating this integral over all of the little dq's will just give us capital Q. So the electric potential at the center of this ring with charge capital Q and radius capital R is just kq over r. Look at how simple that was compared to trying to calculate the electric field like we did previously where we were going down all these rabbit holes. So in the next exercise, consider the electric potential due to the same ring resting in the xy plane, but again at a different point. The point is situated along the z-axis, so the distance from this point to any point on the ring is always the same. What then is the electric potential at this point on the z-axis?